So here we are at the end of chapter 20. So we're gonna close up with relating electric potential to the Gibb free energy and equilibrium constants. So how are all these relations are gonna relate in terms of when a reaction is spontaneous or not? Well, there's a lot of information here, and I'm not gonna read it for you. You can read that on your own later. But I want to point out to the relationship that we have. You already know this one. We learned that one on chapter 19. That's the one that relates the Gibb free energy, the standard Gibb free energy with the equilibrium constant. This is a new one. This is how we can relate the cell potential to the Gibb free energy, where N is going to be the number of electrons involved. Remember at the beginning of this chapter when we were balancing on acidic environment and basic environment, how we had to make sure that the amount of electrons on the oxidation was the same as the amount of electrons on the reduction? That number of electrons is what this N is. And F is the Faraday constant, which you're going to see very soon. So we have a way to relate the Gibb free energy and the cell potential. And then if we do some manipulation and combination, then we come back with a new relationship to find the cell potential in relation to the equilibrium. So we can see how we can relate delta G standard to the cell potential, and we see how we can relate the cell potential to equilibrium constant, which we know we can relate with the Gibb free energy. So when we combine all that, then we come up with the one that I promised you earlier, the non-standard cell potential. And we're going to do that using what we call the Nernst equation, which is going to relate the standard cell potential with the equilibrium constant, the number of electrons, the temperature in Kelvin, the gas constant in energy units, and the Faraday constant. And that's how we're going to be able to calculate the cell potential under non-standard conditions. And all that comes from the fact that delta G relates to the delta G standard by this way. And since we have a relationship for this, we can incorporate all into one formula. So that would be the Nernst equation. And this is what a Faraday is. So a Faraday is just a unit that relates energy, voltage, and amount. And that's where this formula comes from. So delta G standard can be related to the cell potential standard, and then we can relate it to the non-standard by this one. So basically have all those formulas handy and understand where you use each one of them. And once more, we go back to how to determine if a reaction is spontaneous or not. Delta G has to be negative, and the cell potential has to be positive. And the equilibrium constant has to be bigger than 1. By the way, this part here, I'm not talking much about that right now because we're going to do a whole lab where we're going to be covering that. So this is the relationship, or basically that could be on your notes. That relates all the different formulas that you need. Gibb free energy standard with cell potential standard. And you know that the cell potential standard, you get it by doing cathode, the reduction potential for the cathode minus the reduction potential for the anode. We can relate the Gibbs free energy to the equilibrium constant, which means that is the same as that. And when we transfer the natural logarithm and mathematically we convert it into the base of 10, then the Nernst equation looks like that. So you can relate all those formulas like that. And this is what we were talking earlier. When to determine that the products are favored or that the reaction is spontaneous. And then we can talk about something else that you already know. We can talk about Q. And what Q is going to be on this case is when you have a cell potential, when the conditions are not standard, and most of the time what we do is we change the concentration. Instead of being 1 molar, we use something else. We can manipulate the amount of power that you can get out of that cell by playing with the concentrations. So we know that the delta G standard is based on 1 molar concentrations, which is also what you use for the cell potential standard. But if it's not a standard, then it's because you're changing the concentrations. So remember, come back and read this at your own leisure later. So here's the Nernst equation on the most practical way of using it. And this number here is just the temperature, the gas content value, and all that combined into there, in addition to the factor that goes from natural logarithm to the log of base 10. So this is how you find the standard potential, the cell potential for non-standard condition, which is the one you can use to manipulate the amount of voltage that that battery can put out. And if you know this equation, you notice that that's very similar to this, but the only difference, this one have the equilibrium constant, this one have the quotient factor, which is when the conditions are not standard or it's not at equilibrium. And then you can use your math to solve for the equilibrium constant. So let's look at this situation here. A standard versus non-standard. A standard means concentrations are 1 molar, temperature is 298 Kelvin or 25 degrees Celsius. And the atmosphere, if it was a player, it would be 1 atmosphere. So this one is my standard because it meets all those requirements. And under those conditions, this battery generates 1.10 volts. And that's the one that we calculated earlier in one of our problems when I first introduced building a galvanic cell. The second one, the non-standard, the only difference is that we are no longer having 1 molar concentration. So therefore it's not a standard, and that by itself causes the voltage to be higher. So by playing with the concentrations, you can obtain more power out of a battery. Not much, but more. That could be more than enough for something really, really small like a biomedical device or something like that inside your body. So let's see how we can put all this into practice. So what this question is saying is using the Nernst equation, so we're dealing with most likely the only time that there's a practical use to use the Nernst equation is when you have non-standard conditions. Determine the cell potential at 25 degrees Celsius when there's a concentration of 1 molar of HCl. So this is acidic. So it will most likely be nice to be thinking, I probably have to do a balance equation under acidic conditions. And then we have to use this formula. So if we're going to use Q, that means that we have to know the products and the reactants, so we can do products to the power over the reactant the same way we do K. So we better come up with a balance equation first. So what is reacting here? Well, this is the oxidation. So the zinc is being oxidized. So we got zinc 2 plus. Sorry. The zinc is being oxidized, so we got zinc solid combining with the copper that is being reduced, combining with copper 2 plus aqueous, and that should produce zinc 2 plus aqueous plus copper solid. So I had to balance this under acidic conditions, right? Because that's what we have, acidic condition. So my zinc, so that's when I break it into the half reactions. My zinc is going to become zinc 2 plus. This is how I'm also going to find how many electrons are being transferred. And my copper is going to become copper solid. So the first thing I do, I check for the atoms. 1 zinc, 1 zinc. So that's balanced so far. The copper, 1 copper, 1 copper. So that's balanced so far. Do I have any oxygens in there? Remember, I'm going for acidic balance. So I'm going to see if I need to add water and then add H plus to balance and so on. But there's no oxygens there. So even though it's acidic, I don't have to do any of that because there's no oxygens to balance. So the only thing I have to make sure is that the left side charge is the same as the right side. So the left side charge is 0. The right side is 2 plus. So I'm going to have to add 2 electrons. And that will make it 0 on both sides. The same thing happens with the copper. And that will make it 0 on both sides. So that means these reactions involve the exchange of 2 electrons. So N equals 2. And my Q is going to be products over reactants. So concentration of copper, concentration of zinc 2 plus over the reactants, right? Zinc and copper 2 plus. However, the zinc is solid and the copper is solid, so that doesn't go there. So the copper solid has to go, the zinc solid has to go, and the only thing I'm going to have are going to be my aqueous. So that's going to be my Q. And it's all 1 to 1, so it's to the power of 1 to the power of 1. So I have my Q, I have my N. So my N, I have it. My Q, I know how to do it. So the only thing I need to find is my E cell, which is going to be the standard reduction potential of the cathode minus the anode. And if we remember right, we did that earlier, right? The zinc was going to be negative 0.17 or something like that, I remember. and the copper was going to be 0.34. So the copper was going to be the cathode, the ink was going to be the anode. So when I do E cell equals standard reduction potential of the cathode, which is where the reduction happens, so for copper 2 plus, minus the standard reduction potential for the zinc. But what I find on the table is the one. Remember, the table only shows reduction, so I'm gonna do it for the zinc 2 plus. And when I do the operation, which we had done before for this reaction, the answer is gonna be, that's what we're doing here, right? The answer is gonna be 1.10. So E cell equals 1.10 volts. So given all that, I have my E cell, 1.10 volts. I have my Q expression, and I have the values for that. Zinc 2 plus is going to be 0.010. So that's what goes in there. 0.010 molar. And my copper is going to be 2 molar. And that's what goes in there, 2 molar, which means my Q is going to be 0.010 divided by 2, 0.005. Remember, the Q have no units, right? It's like the equilibrium constant. So I have my E standard, I have my Q, and I have my N. So let's solve this problem. So that means the cell potential at non-standard condition is going to be 1.10 volts minus 0.0592 volts divided by 2 log of 0.005, which tell me under these conditions, my standard cell potential is going to be, just give me a second, the log of 0.005 multiplied by 0.0592 divided by 2. So that's going to equal 1.10 minus 0.068. So 1.10 plus 0.068 is going to equal 1.17 volts, which is the problem that we had in there. So you see how we apply the Nernst equation for non-standard conditions, and we get our E cell for non-standard conditions. So this is what we call a concentration battery, where you can change the voltage by changing the concentrations of the solution that you're using. So remember, the first thing I had to do was to write the overall equation, then break it into half, and make sure I balance it. And since I saw that, I was thinking all the time acidic conditions, but there was no oxygen to balance or anything, so it wasn't really a factor for me. However, on your daily work, there's oxygens involved. So make sure you balance according to acidic conditions. The 1.0 molar is telling you that these are acidic conditions. And here you have the concentrations you're going to use. And remember, you find all these half reactions on the appendix that I showed you here, which is on your packet on Canvas, and it's also on your textbook at the end of the book. So after you do that, then you should be more than able to do the same thing with this reaction, balance it, determine the number of electrons and all that, and then you should be able to have the mathematical skill to apply any of these formulas. And the answer is here, so you know you're doing it the right way. And then you have another one where you can continue applying your prowess of math skills and determine the equilibrium constant. So find the equation that relates equilibrium, which could be this one here, right? And mathematically solve for the equilibrium. Remember, you always have to balance the reaction first. And with that said, that's how we relate cell potential, Gibbs free energy, and equilibrium constants. Which bring us to the end of this chapter, where we learn first. We first have a review on how to keep track of the oxidation numbers, something you learn on General Chemistry 1. Then we use those skills to balance on acidic environment and basic environment. Super important, as you saw, we have to use that at the end of the chapter. We learn a lot of terms about electrochemistry, like anode, cathode, reduction, oxidation, salt bridge, electron potential, reduction potentials, and all that. We saw how we can build a galvanic cell. We said that we're going to study electrolytic cells later. And we saw how to determine the cell potential first under standard conditions, just using the tables on the appendix. And now you saw how to use the Nernst equation to determine non-standard conditions. And then we just learned how to relate all these thermochemical dynamics to cell potential also. And that brings us to the end of the chapter. Do you realize we only have one more chapter to go, and the course will be over? And the chapter that we have remaining is super interesting and super easy. You will be amazed how easy that chapter is going to be. So until next time, you will be listening to this chapter most likely after your test number 3. So wishing you the best as always. Let me know if you have any question, please. And remember to study your workshop handout so you can come prepared in case that we have a quiz. See you later. Take care.